Sprawling legacy enterprise software codebases are silently collapsing under their own massive weight, consuming up to 80% of total IT budgets just to maintain baseline corporate operational functionality. This invisible structural decay represents the modern technical debt crisis, an operational bottleneck that systematically chokes continuous deployment pipelines and paralyzes critical digital transformation initiatives across global enterprise industries. Traditional software engineering models have officially reached an absolute breaking point regarding system maintenance limits, forcing corporations to waste valuable talent on fixing repetitive architectural decay patterns. When core software architectures degrade over time, enterprise organizations face catastrophic delays in feature deployments, turning minor codebase adjustments into high-risk engineering operations that threaten system stability. The primary issue stems from deep structural interdependencies within multi-generational monolithic applications, where modifying a single line of old code can trigger completely unpredictable downstream systemic failures. Human engineering personnel spend their valuable operational hours manually tracing complex dependency maps, debugging archaic syntax errors, and managing fragile regressions rather than building highly innovative product features. This exhaustive manual intervention drains corporate capital reserves and burns out talented software developers who find themselves trapped acting as digital firefighters instead of creative systems infrastructure architects. Extensive industry evaluations emphasize that modern code-based complexity limits frequently exceed human cognitive management capacities, creating a massive wall of technical friction for internal information technology operations. As software systems expand globally, the sheer volume of unmapped continuous documentation, updates, and interconnected application programming interfaces creates severe operational vulnerabilities that threaten long-term enterprise scalability. Traditional automated testing setups fail to resolve this fundamental crisis, as they merely identify operational errors post-compilation without offering actionable programmatic solutions to repair the underlying broken logic. Enterprise applications consequently remain frozen in archaic states, unable to integrate modern cloud capabilities or utilize advanced, high-throughput database frameworks required for real-time transactional data analytical processing. Security vulnerabilities simultaneously compound within these unrefined legacy environments, creating massive attack surfaces that open-source dependency scanners struggle to map or patch effectively without breaking live production systems. Corporate leadership frequently responds by allocating more engineering headcount to the problem, yet adding human labor to complex software projects often worsens delivery timelines due to communication overhead. The industry requires an immediate paradigm shift away from reactive human debugging toward an entirely autonomous, proactive methodology capable of healing enterprise code ecosystems silently at massive scale. Enter the architecture of self-healing code ecosystems, a revolutionary approach leveraging localized agentic validation frameworks to diagnose, test, and rewrite production software errors completely independent of human intervention. This advanced framework deploys specialized artificial intelligence agents directly inside the local development environment, continuously monitoring code health metrics and calculating syntax optimization trajectories before compilation occurs. By utilizing structured system interconnection documentation, these autonomous agents maintain highly persistent state tracking during complex code-based refactoring operations, ensuring seamless transitions across multi-tenant enterprise software networks. When a software error is detected within the repository, the Agentic engine constructs an isolated abstract syntax tree to mathematically analyze the broken logic without altering global production branches. The self-healing ecosystem then executes an internal compilation validation loop, utilizing advanced reasoning engines to formulate precise code patches that resolve the diagnosed failure vector cleanly and efficiently. These localized patches are subjected to intense, automated unit testing matrices managed by the Agentic framework, verifying that the new logic matches the exact expected functional specifications required. By automating this verification process locally, The system ensures that no corrupted, unoptimized, or regression-heavy source code can ever escape the local workspace to pollute upstream master repositories. To guide this complex migration pattern safely, enterprises can align their strategies with systematic enterprise architecture methodologies, ensuring that autonomous agentic refactoring seamlessly integrates with existing systems. This structural alignment ensures that autonomous refactoring preserves foundational business logic rules while decoupling complex application dependencies across the entire corporate technology stack footprint without human interference. Furthermore, the integration of these AI-native agents relies heavily on open standard, stateless tool-calling communication channels established directly between the artificial intelligence models and the underlying production environments. This technical setup allows self-healing agents to query structural metadata maps securely without running into memory access bottlenecks or exposing sensitive intellectual property to external public networks. The agentic system operates through continuous reinforcement loops, learning the unique stylistic guidelines, architectural conventions, and precise security compliance mandates specific to each distinct corporate development team. Instead of relying on fragile heuristic rule sets, the platform applies neurosymbolic logic models to understand both the high-level semantic intent and the low-level execution mechanics of code bases. This dual-layer understanding allows the self-healing ecosystem to perform complex optimizations, such as converting bloated legacy monolithic functions into sleek, containerized microservices ready for cloud-native deployment. When navigating highly intricate entity relationships across legacy systems, the architecture incorporates precise knowledge graph schemas to control outputs, decoupling core logic from raw model weights directly. Controlling generative outputs prevents the generation of hallucinated syntax variations that could jeopardize continuous integration pipelines, ensuring absolute mathematical precision across all automated code refactoring workflows. The resulting system functions as an autonomous quality assurance engineer, working at sub-second processing speeds to eliminate technical debt before human developers even notice a syntax discrepancy. This transformation effectively shifts the paradigm of software development from manual composition and tedious debugging to high-level system intent definition, redefining the traditional lifecycle of software application maintenance. With the autonomous agentic infrastructure securely established, the measurable operational and economic impacts ripple across the entire corporate structure, transforming cost centers into engines of continuous innovation. Deploying self-healing code ecosystems compresses system debugging timelines and IT maintenance operational expenses by an astonishing 80%, radically optimizing the corporate technology balance sheet immediately. This massive fiscal optimization allows enterprise organizations to reallocate millions of dollars from routine system upkeep towards strategic research, development, and customer-facing software feature innovation initiatives. Prioritizing systematic technical debt reduction over short-term patch solutions significantly accelerates corporate productivity indices, preventing the rapid economic depreciation of core digital assets and legacy technology infrastructures. Long-term economic models confirm that autonomous remediation safeguards software lifecycle value, helping large enterprises scale their digital operations efficiently while avoiding the traditional overhead of manual maintenance. The structural transformation extends deeply into the labor dynamics of the enterprise, fundamentally redefining the daily operational roles and long-term career trajectories of human software engineering personnel. Rather than displacing human technical talent, this technological shift accelerates upskilling speeds, transitioning entry-level programmers away from repetitive syntax correction toward serving directly as high-level architecture overseers. Human engineers assume complete governance over the agentic networks, reviewing autonomously generated pull requests, setting global security parameters, and defining the overarching structural goals of the corporate enterprise. This transition elevates the human worker to an essential evaluator, maximizing their creative cognitive leverage while eliminating the mundane, error-prone tasks that traditionally caused widespread engineering exhaustion. Operational reliability reaches unprecedented levels as autonomous verification loops systematically eliminate human error from the deployment cycle, ensuring that software builds remain consistently robust and completely compliant. System downtime events caused by misconfigured code updates vanish entirely, protecting corporate revenue streams and preserving consumer trust across digital platforms and critical public-facing transactional services. The broader business ecosystem experiences heightened agility, allowing product teams to rapidly experiment with new concepts and deploy production-ready updates to global users within minutes instead of weeks. By transforming software codebases into highly adaptive, self-sustaining assets, enterprises successfully future-proof their operations against unexpected technological disruptions and competitive market changes in the global digital economy. To implement a fully operational self-healing code ecosystem, corporate technology leaders must follow a rigorous, phased deployment roadmap anchored in established cloud architecture and software engineering governance patterns. The foundational step requires connecting autonomous self-healing agents directly to pre-commit Git hooks, creating an automated, localized gatekeeper that inspects code modifications before they are ever staged. This isolated testing layer runs unit scripts inside containerized execution sandboxes, ensuring that any faulty logic or formatting discrepancy is immediately intercepted, diagnosed, and repaired right at the source. Enterprises should structure these isolated, microservice execution layers by utilizing comprehensive architectural governance maps, guaranteeing that containerized validation clusters scale efficiently across hybrid cloud infrastructures globally. Maintaining strict isolation barriers protects core development systems from accidental execution errors, ensuring that autonomous agentic code generation occurs safely within designated development environments across the enterprise. Once local integration is secured, the next phase involves connecting the agentic engine to continuous integration pipelines, allowing automated code refactoring to systematically eliminate legacy software bloat across repositories. To maintain maximum operational visibility, developers must implement advanced monitoring blueprints, tracking error budgets precisely, and establishing sub-second monitoring metrics across all automated self-healing software workflows. Applying robust site reliability engineering frameworks allows organizations to monitor dynamic agent resource consumption and ensure stable runtime environments for large-scale code optimization and architectural transformations. This extensive real-time telemetry ensures complete operational transparency, letting human technical leaders audit agentic patch performance and measure code technical debt reduction trajectories through centralized analytics dashboards. As automated code refactoring scales across the corporate enterprise, the long-term remediation of legacy software bloat becomes an organic, ongoing background process requiring minimal operational oversight from management. The era of manually wrestling with archaic code systems is officially over, replaced by a modern paradigm where codebases maintain themselves dynamically to support continuous digital transformation goals. Organizations that embrace this autonomous framework can confidently deploy software updates at high velocity, knowing that local agents are constantly safeguarding repository health against unforeseen technical errors. This capability creates a sustainable competitive advantage, enabling enterprises to outpace market competitors while maintaining lean, highly efficient IT infrastructure support operations across all business departments. The future belongs to autonomous, self-healing digital infrastructures that continuously optimize themselves for peak performance, allowing human intelligence to focus strictly on pioneering next-generation software product breakthroughs. Subscribe immediately to our Enterprise Tech Brief to command tomorrow's technical leverage, ensuring your enterprise successfully deploys advanced autonomous software architectures to drive unstoppable growth and digital transformation. Zero hype, pure architecture.